Okay, ladies and gentlemen, let's start. So I'm going to talk a little bit awkwardly because I want to be here and to make sure that everybody who is online can hear me, but I'm also going to make sure that everybody in this room can hear me. Okay, so super nice to have you all here, both to the people in room and also to the people online. This is an idea which rose to prominence. Sorry? I have turned on the recording, don't worry. Yeah. So this is an idea which rose to prominence last week in Hinode meeting. I spoke with some people online and offline, and we thought that it would be a good idea to make maybe a small workshop, physical workshop at some point about applications of machine learning to solar physics. And then we actually thought, okay, it will take some time to write the grant, to get the money, to organize all these things. Why don't we start something which is similar to ESPO seminar, which you all know about, and make it online so that everybody who wants can participate there, and then we can have different speakers from different fields talking about different things every day, and sometimes we can also Andreas, I think that you logged on that computer, but everything should be working fine. Yeah. So anyway, so that we can also share some resources, we can share some tutorials, we can share codes on GitHub, and we can also just sometimes make these meetings and sit and talk about some it doesn't have to be a talk every time. It can be just a spontaneous discussion. So we really want to make it super informal, and as you will see, my lecture is it's not a lecture, the presentation is going to be very informal, and it's made very ad hoc, but it's just to introduce you to some things, to show you what I'm doing, to hear input from you, and maybe if you want to start doing this and you don't know how, I did this basically on my own. I'm sort of self-trained, and it's very easy, and I think that I can maybe help you, but if somebody just nudges you a little bit, you can get into this. Okay, so in general, this is basically what we want to do, right? We want to talk about machine learning, about neural networks, about other things there. We want to keep the community engaged, and I think it is especially important, for example, for people who are maybe alone and the only person in their institution who wants to do these sort of things. So then it would be very good for them to have these online meetings, because then they can obtain a lot of help this way. And also, ultimately, we want to organize some physical meetings, some workshop, so we don't have to really think about it right now, but keep it somewhere in the back of your head, because the moment will come. Okay, what do I want to do today? I want to show you what I was playing with during the last couple of weeks, actually the week before Hinode meeting. For the people who want to start but they don't know how, I just want to show you that to start is very easy, probably to understand and to optimize and to really use it in the proper way. It is much harder, but we all have to start from somewhere. And then in the end, I want to devote a lot of time so that we can all, both in room and people who are online, we can discuss and make a plan how to make these meetings better and how exactly to organize all these things. So today I'm going to give a talk which is maybe going to last 20 minutes. We can discuss the science behind it for like 10 minutes. And then I would say that we can discuss the future steps of these online meetings for like next 20 or 30 minutes, but it doesn't have to be like that. A special shout out is to people from Vector Magnetogram Workshop. A few of them are here with us today, and it just happened that we had this workshop for 3 days here in Max Planck, and there was a full session dedicated to machine learning, and so they just stayed here for a couple of extra hours to attend this presentation. Okay, so let's start talking about science, and yeah, let's see what this is about. Okay, so first, most of the people in the room know that. Maybe some people online don't know that my specialty or my main field of interest is spectropolarimetry, and namely spectropolarimetric inversions, which are a way of quantitatively extracting the properties of solar atmosphere from the observed Stokes spectrum. So I will first have to spend a certain amount of time getting you acquainted with this thing, and it will be, I think, especially important for the people who come from different fields, and I think that also we have some people attending who are not even solar physicists at all. So in the solar spectra, we have these features, and these are spectral lines. These spectral lines here look super beautiful because they are synthetic. They are calculated from a state-of-the-art numerical simulation performed by Murray code. Okay. And the spectral lines when we resolve them, I mean, the solar spectra, when we resolve it spatially, it varies from point to point. So today we have a very accurate, very big telescopes, which can resolve solar surface to very small details. So let's say less than 0.1 arc seconds. And then when we look at the solar structure, it really looks something like this. So today's simulations are really, really good. So you can see in detail the granular lanes and granules and intergranular lanes, and the spectra of, strictly speaking, spectra of two different points in the solar atmosphere is going to be different. So what am I plotting here? This is the temperature in the photosphere. So you see that the granules are hotter, intergranular lanes are colder. There are some regions which are much, much colder. And here on the right is the velocity distribution in the photosphere. So as you know, the plasma in the granules is going up. The plasma in the intergranular lanes is going down. Okay. This is what we got from the simulation. But what we want to do is we want to observe the sun and to infer these quantities. Right? We want to measure them somehow, and we want to ultimately to compare them with simulations in order to understand what is happening in the sun. But we cannot observe these things directly. We can observe the spectral lines and see the connection in between them. Okay. The problem is that the only exact theory that we have to describe this connection is the theory which does forward modeling, so to speak, and is the theory of stellar atmospheres and radiative transfer. So basically, if I give you a model of the atmosphere, and by the model of the atmosphere, I mean the stratification of temperature, velocity, and magnetic field density in one of the pixels of this simulation, then I can use various physical approximations in order to calculate all the relevant quantities that I need. I'm not going to go too much into detail with that because we have a limited time, but in principle, there is a theory which describes connection between the model of the atmosphere and allows you to numerically calculate the polarized spectra which emerges from such an atmosphere. Our goal, however, is exactly the opposite. We have the observed spectra, and we want to find the most probable atmospheric stratification behind that. Right. So just to convince you that the information really is in the spectral lines, I want you to look at these two different spectra. So the spectra from a hot region, okay, this one here, it has a higher level of radiation, right? And also, if you look very carefully at that point here, we have blue shift. So it is also shifted a little bit toward the blue, while the other spectrum from the cold region has lower. I mean, it radiates less, and it is red shifted. So the lines are a little bit shifted toward the higher wavelengths. However, what we need to know about spectral lines, and what is very important, and why they are the richest source of information that we have when we observe the solar atmosphere, is the fact that they are not only sensitive to the temperature and the velocity at one layer, but also on the multiple layers. So now I'm going to plot the distribution of these two quantities higher in the atmosphere, above the photosphere, and this is what it looks like. So we have completely different temperature stratification and velocity stratification, and all this depth dependence is contained in the lines. So basically what we want to do is we want to, since we have this sort of spectrum for each point in the field of view, so we have a data cube which is xy lambda. We want to go from the data cube of xy lambda to xyz, basically. It's not strictly speaking z, it's a little bit more complicated than that, but for the moment, just imagine that we want to use the valence dependence to probe the depth dependence in the solar atmosphere. How do we do that? Hold on. I think I want to show you this first. Yeah. So over the years, people have developed this approach, which we call now spectropolarimetric inversion. And the spectropolarimetric inversion is basically you start with a model atmosphere and you somehow iteratively adjust it until your observed spectrum is fitting the calculated one. So here you can see a very ideal example where I have these mock observations marked with blue lines, and then my inversion scheme is adjusting the spectra and is adjusting the temperature stratification of the atmosphere until the I, Q, U, and V of the radiation. So we are not only observing the intensity of the radiation, we are also observing the polarization state until I agree with the observed ones as good as possible. Of course, here they can agree basically perfectly. And here you can see how our metric, which is in 99.99% chi-square, how our metric is being decreased because the fit is getting better and better. Okay. The problem is that this process is very demanding. It is demanding why? Because all the calculations are numerical. Further than that, some of the spectral lines which form higher in the solar atmosphere, they have very complicated methods of formation. They're formed by scattering, and scattering is inherently non-local and non-linear process. So you really need to push and to iterate and to spend a lot of computational time just to evaluate your forward model. Sometimes you need seconds or even minutes to do one calculation of the spectra. For example, in the case of these very, very high forming lines, such as the iris lines, etc. Okay? So it's very much not easy thing to do. And that is only for one calculation. So then you somehow iteratively need to correct your spectrum until you obtain a good fit. So it really, really requires a lot of time, right? So usually what we do here is we say, okay, the best that we can do is that we simplify the atmosphere somehow, either by employing some sort of regularization or simply by decreasing the effective number of degrees the freedom the atmosphere has. Because remember, I didn't specify it explicitly, but atmosphere for us is basically just a numerical array, all of the quantities along the line of sight. Okay, so the best that we can do is to come up with a fast and approximate and a rough model for our line formation, to be able to calculate the derivatives of the observables to the model, and then to employ some derivative-based method to do this minimization and invert, as we say, our data. For this thing, this concept of nodes is going to be important, because that is the way in my code, in our code, we have chosen to parameterize the atmosphere. So instead of describing the atmosphere with this whole stratifications here you can see the examples for the temperature and the magnetic field. We say, okay, the atmosphere is determined by these 4 points here, which are free to change. And then in between, we have some sort of interpolation, and outside we have some sort of extrapolations. Okay, so instead of, maybe here I have 40 or 50 points, instead of treating all of these 50 points separately, I only treat these 4 points here separately, which are called nodes. So then your model is determined by the positions and by the values in these nodes. These are your model parameters. And then you have a model which has maybe 10 or 15 or 20 free parameters. From that model, you can calculate your spectra. You can calculate the derivative of the spectra to these model parameters, and you can employ derivative-based minimization. The problem with the derivative-based minimization, okay, so first here is an example how it works. This is the example of the real data from the SST, and it is obtained by Michiel with the very sophisticated spectral restoration technique, which gives us great spatial resolution, etc., etc. But the point is the following. You have, in this case, we have used intensity and circular polarization in the line. So here I have only plotted some representative wavelengths. And from these, we get the depth stratification of the temperature. So here you can see familiar granulation pattern. Here you can also see familiar reverse granulation pattern and the plage. Then also here you can see the convective velocities deep in the, not very deep in the photosphere, slightly above the photosphere. Here you can see some velocity signature, which we don't even know what it is, but I mean, this is not the point of the talk. And here you can see how the magnetic field is changing with height. Okay, so basically we see, by looking at the lines and their polarization and the wavelength dependence of these two, we get to map the atmosphere in depth. Okay, the problem is, and this is basically what we do. So each of these pixels has a spectra in Stokes I and Stokes V, and we try to fit the synthetic to the observed one. Okay. The problem is that this is, yes, maybe. You can do that, for example. That is, but I mean, in principle, people usually start from one model, which is universal, and then usually these things converge quite well. But in principle, you could start from a model which comes from the simulation. But the point is that simulation gives you a lot of models, right? Because the cube has a lot of pixels, and they can be quite different with each other. Right? So all the thing that I'm describing here is done on pixel by pixel basis. You analyze your observations pixel by pixel. I'm almost sure that when Andres gives talk in 2 weeks, that you are going to hear something much more mind-blowing. But okay. So the problem with this process is that it's very slow. Even if you manage to do one iteration of the inversion, so it means one correction of the parameters in 1 second, and assume that you in 10 iterations you converge, you get a good fit, which is super stable, super fast, and you want to invert a field which has 1,000 times 1,000 pixels, it's going to take you 100 days of computing time, which means 1 full day on 100 processors. And we are not super far away from having a lot of these fields observed in 1 day. So with DKIST, with integral field units, with new methods of observation, we are going to be getting a lot of data. Additionally, and for those of you who were in the meeting, remember the talk of Alberto. This 1 second is super unrealistic for some spectral lines. For example, for magnesium H and K lines, which are formed in the super high in the atmosphere, this 1 second is science fiction. You need a lot of time to invert these lines. So you can't spend so much computing time doing that. So then I think many people came to the similar idea. And the idea is the following. When we look at the sun, the things are somehow clustered. You don't have some very crazy atmospheric models. Every granule is more or less similar to the other granule. Every intergranular region is more or less similar to the other intergranular region. So if I learn something about a small piece of the atmosphere, but for some reason I want to study a big piece of the atmosphere, there should be a way for me to somehow very quickly do that, to very quickly accelerate this thing. And that is where we can apply some machine learning techniques. So there were people who were using these things already for that. So as I said, Alberto already gave a talk on this, but some other people from solar physics community have used machine learning for some other ideas. And I'm sure that we will hear about these things during the upcoming talks, but just if you are already interested, check out the papers by Andres Asensio, Carlos, and Iker. And they studied, for example, enhancing HMI images or measuring the plane of the sky, velocities of plasma in the solar atmosphere, etc. What I wanted to do here was something different. I basically wanted to teach a neural network to train it on the existing results of inversions. So for example, I have a lot of pixels that I want to invert. What I wanted to do is to invert a part of these pixels and then train a neural network to repeat this thing for me. To basically find out how the observed spectra maps to the model atmospheres and then do that again for me. So I started looking for that because in solar physics, people tried it a long time ago, but they mostly used their own made neural networks, and these are not convolutional. And apparently convolutional neural networks should be good there because convolution somehow detects the features in the spectra and in general in the images. So the thing that I found most similar to that was this paper here by Parks and collaborators, where they used convolutional neural network to detect presence of Lyman alpha absorption, as far as I remember, in the quasar spectra, and then to characterize the column density of that neutral hydrogen which is absorbing, and to measure some other properties, to do some classification, doesn't matter. So basically what we want to do here is we want to teach a neural network we want to teach it the mapping between the spectra and the parameters. Okay, so what does neural network do? And this is now where I'm starting hand waving because I was just learning on the way. So after the talk is done, I ask for your contribution and better explanation. Basically, it's a chain of transformations which connect the input and the output, and these transformations are very simple. They are linear, they are nonlinear. For example, convolution is an example of a linear transformation. Then you usually, after that transformation, you apply something which is called activation, and that activation is something which is nonlinear, so it allows you to capture better the nonlinear mappings. So then let's say I align a certain amount of these neurons next to each other. So for example, I do one operation on my data, I get some result. I then do another operation, I get some result. Another, and then on the end, I'm supposed to get the parameters. So what I start with is the spectra on my side, the parameters are on the other side, and then I somehow need to tune this in between. And basically the process of training of the neural network is essentially some sort of linear regression which minimizes the parameters of these transformations so that this connection here is made as good as possible. Basically what network does is it goes backward forward, then it evaluates the difference between the actual output and the output it would make, and then it corrects the parameters in between. So perhaps at some point we could have a really deep and long and detailed talk about how neural networks work. As I said, the convolutional layers here they're a relatively new thing which people started exploiting recently, and they are very good at feature detection. And the features in our context are spectral lines. Okay. So basically, this is again a zoom on the neural network from this paper of Parks and collaborators before, and my neural network, which I'm going to show you, looks super similar to this. So you have a spectra. The spectra is convolved by some kernel function. You get the output of that. Then there are these pooling layers in between, which basically just somehow sparsify your data in a way, or bin, or I don't know how to say differently. Then you have another convolution and another, and then you have these fully connected or densely connected layers, which basically help you to estimate the parameters. And then there are a lot of coefficients here in between, and you iteratively correct these coefficients. And then when you train the network, you expect it to be able to do these sort of predictions for you afterward. Okay, so basically what I did is that I said, okay, I will take these observations, where I already did the inversion. Okay, I will take all the spectra here as the inputs. I will take all the, okay, maybe one more slide back. I will take the spectra in these points as inputs. I will take these values of physical parameters and at nodes as outputs. I will train the network to do it. And then I will run the network on all the observations. So this is still not full field of view. I don't know why, maybe I just didn't assemble it or something, but this is much, much bigger number of points than I showed you before. And you can see that, at least by naked eye, until you look like very closely, you would say that this looks very good. And it really does look very good. These things look exactly like something that you would get from real inversions, except it's infinitely faster. Once you train the network, it literally gives you back the results instantaneously. At least in this case, which is very, very simple. Okay. The problem is that if you made some errors in your inversion original that you used to train your data, all these errors will be still there. So for example, this is important thing is that my particular parameterization of the atmosphere was not good enough. So I was getting some weird oscillations of magnetic field. And then these basically neural network learned these oscillations and then applied them to the rest of the data. Okay, but we can discuss about that later. Okay, so the question now is going to be, especially from people who maybe don't have a lot of people to discuss it at their own institute, is okay, how do we do this magic? I'm strongly against all the black boxes and everything. And as I said, Michiel and I, we developed our own code for spectropolarimetric inversions for these 4 years while I was working here. But I have to show you that basically everything that you want to do for these neural networks can be done in these 10-ish lines. So there is a package for Python, which is called Keras, which works on this, another package which is called TensorFlow. And literally everything that you need to do is to load your data, normalize it, so choose your data cleverly, normalize the data appropriately, and then you make neural network and train it and predict from it. And here, basically, you can see exactly what I did. I put some convolutional layers to this model. I add some densely connected layers. They have different sorts of activations. And I fit it. I use the mean squared error. So I want my measure of quality of the training is that I want the predicted spectra to agree as good with the original spectra from the training set. And then I let it run for some time. And then when the model is done, you save it to a hard disk in a small file. Then you load that file and you can invert billions of pixels that way. Yes? Yes. And then you apply to new spectra. Yes. Yes. And so how would this compare to inversions if you've done the two inversions? Good. I will show you later on another example. Good. There are discrepancies, of course, and for example, if I use this to synthesize the spectra and compare the chi-square with inversion, it would not be as good, because of course the neural network just approximates this connection somehow. So it okay. So Mark says that he cannot hear questions, so probably nobody can hear questions. I'm gonna reply what I'm gonna repeat what Mayuk asked. So the question was, how do the results obtained from neural network compare with the results of the original inversion? And then was my answer, which you probably heard. So the agreement is very good. I will show you the agreement on another example now, but of course it's not as good, because the way I understand it is that the neural network learns this mapping between the parameters and roughly learns this mapping between parameters and observables. But with inversion, what you do is that you go down the chi-square all the way, right? You really go down and minimize it all the way. So it will always going to agree better than what neural network is. But let's talk about it further. So I wanted to show you this as a super simple example of the neural network, but with this I obtained what I obtained. And then if you want to start immediately, when we finish this talk, you want to go to your home, make a big lemonade and start doing neural networks, you can, the tools that I use are TensorFlow and Keras. And there is this example here. I will try to put a talk online or to put this in the notes or simply send it to the mailing list. There is a very simple tutorial which is focusing on some image recognition, and from that you can make everything. But basically the keywords are elite data science and Keras tutorial. Okay, but also the page of Keras is also super informative, and you can learn a lot of things there. Okay, good. So let's talk about some more specific things. This is the same example. So basically the question now comes, how do I, my question which I have for you is, how do I verify that my neural network is well trained? Because there are these quantities which the trainer spits out, but I don't trust them. So I really want to see if my neural network can recognize what is behind. So my idea was, the simplest thing that you can do as a sort of a sanity check is, okay, I train my network on this data, and then I ask the network again what is in this data. If it doesn't return me more or less what I trained it on, something is wrong. And so here you can see some examples. So what I'm going to show you now, basically the same thing as I showed you before, except it is now on the synthetic observations from an MHD cube. Why, it will be clear in a couple of minutes. What I do here is I have a 288 times 288 cube. I synthesize all the spectra there, so it is like, what, almost 100,000 spectra. Then I select 10,000 spectra on these 10,000, and I don't even select them very carefully. In principle, what you could do is you could do some K-clustering, find the representative spectra and train there. I do even more stupid thing. I just cut the slice, just cut the corner there, invert it using inversion code as good as possible, and then train the network on that. And then when I ask the network to return me back I feed the network again the spectra from this small patch, and I ask, what do you see? I get very good agreement between the original values of parameters and the inferred values of parameters, except that the maps, and you see that because we are focusing on high resolution solar spectropolarimetry, we always show some maps. The maps are smoother. And this is something which for me was super tricky. How can a network know that the map is supposed to be smooth? And my only explanation that I have is that the spectra are similar among themselves. And then since the neural network is really learning he's learning how to map. It's not learning anything, it's imitating. It's learning the mapping between the parameters and the spectra. It somehow avoids all the noise which is there, and because of the noise we are getting these little salt and pepper noise here, because the noise in observations translates in us ending in maybe not the right minima and missing the original model which actually is there. So this is something that I would like to explain to myself. Yes, that was my very good. We can also use questions this way. That was my logic. I was expecting it not to be smooth because each pixel is independent. But the point is that the image of observables is smooth. So somehow the neural network smoothly maps the things and gives you back the smooth map of parameters. Does it make sense? Can you turn the microphone and tell us?
Well, it seems to me that the neural network doesn't know anything about neighboring pixels, and so any smoothing that's happening ought to be an artifact.
Okay, yeah, I also expected that, sort of, but I mean, every pixel is fit independently. So these are the values that the neural network thinks that these values are. My explanation was, so we can discuss it, we should discuss this in further, is that somehow smooth, let's say that you have certain model which produces certain, so now it's really weird because I'm looking at the computer, but Mark is not there, so I also can look at you. My logic was that you have spectra, you have parameters. If you change these parameters slightly, we expect the spectra to change slightly. So we expect somehow to have smooth transition as you slowly change your model, your observables change smoothly. But the point is that because of the noise, when you do the inversion, you can end up, although your two neighboring spectra look very similar, because of your inversion method, which maybe gets stuck somewhere, or because of the noise, which is super extraordinary somewhere, you get some solution which departs a lot from the original atmosphere there. And then my interpretation is that the neural network is not hampered by these noise effects. Does it make more sense now?
But in that way, you're saying that the neural network is better than the inversion.
Yeah, I think it makes perfect sense. And you can take an image and add some noise on it. Yeah, a little bit of noise. If this noise is removed by your problem.
So we have a lot of questions, but can you tell me again if you heard Sasha's and Sebastian's remark or no?
I didn't hear any remarks, but my question was, did you try to see if the neural network smooths a noise-free sort of a model or some noise-free data?
No, not yet. But let's now hear the remarks of people. Can we use maybe the microphone? Will it work?
Or maybe the speaker stand up and go there.
Yeah. So let's go, Julian. Can you
try to shout? I don't know.
or you can ask the question out of the
Yeah. So, but I think this has to do something with what you're saying, because in your final output model parameters, you have parameters for everything, but your measurement of the noise is kind of intrinsic in your goodness of fit, right?
Yes.
So you don't have like a single parameter that tells you this is a more noisy data. And if you can you add an extra parameter to tell you, oh, this is more noisy than another parameter? I mean, to give an extra parameter to the neural network to quantify the noise.
Okay, the question is whether we can add another parameter to the neural network to quantify the noise. I'm not sure. Maybe it's better if people come to the microphone and speak, because I'm not sure that I can. This is already discussion, so now, no, but feel free to come and say. So who was the next? Smitha?
Yeah. Just.
Okay. But the microphone doesn't work.
Yeah, it doesn't really work. No.
So in connection with the previously asked question, does it really help if you take a bigger patch so that it has more statistics?
Yes, I expect it. Yeah. You mean for training?
For training, yes, exactly.
Yes. If I take I expect that if I take a bigger patch, that it will work better, of course. But I mean, I'm not complaining here. I'm sort of, I think that this is how it should work in a way. But we need to understand why.
But the answer is yes and no, because there is a case where you how big is the data set that you're training on?
Well, you're coming. I think the answer is yes, yeah, because you cannot train your network to recognize noise. So noise will be averaged out. That's exactly what it does.
No, but
Okay, so Sasha's remark is that the network sort of averages out the noise. And then Sebastian.
But in real life, there's always going to be noise. So
We should not want to know. We just
so
want
then
to
it's
remove
useless
it.
if you cannot quantify the noise. Right?
yeah, but there is a region where you can increase the data when you're training your neural network, and you don't get more information because your neural network is so much trained that you're losing information somehow. So the size of the data that you're training your neural network with is important also. So I don't know if you have studied something about that.
No, not yet. But we can also try that. Mayuk.
Is it possible?
Oh,
Is it possible that features below a certain landscape simply don't get picked up by the neural network and it wouldn't necessarily apply to noise, but in any small scale features and features beyond a certain landscape just wouldn't be picked up? And maybe you need to add more layers. I don't know. And if you train it further, maybe it can pick up some. Maybe it's just missing small scale features.
Yeah, okay, so Mayuk's question was whether this has something to do with length scales in space. And the answer is no, because basically all these images are assembled later. So when trained and when interpreted, the neural network doesn't know what is where. And then Mark's remark was that the noise is sort of averaged over the whole model, which is something also that I think could be the thing. But this is something that I really want to look in further and to see why these things happen. And then Hape?
Fundamental question. So no physics at all involved in the neural network.
Yeah.
Right?
So
Just,
no.
Can it invert for something that it hasn't seen before?
No. So Hape asked, of course, a very good and essential question, which was whether there is physics in neural network and can it invert something that it didn't see before. It can try, but it will probably fail.
So naturally, everything it gives you is a smooth version of stuff that it hasn't seen before, kind of interpolated.
Yes. It exactly gives you the sort of cleverly interpolated version of the stuff that it has seen before.
That it's smooth because it's
That is also sort of
that it has seen before.
Yeah. I don't know. Let's keep this for. Let's finish the talk and then we can go back to this example because this example is apparently very, very good. So what I want to show you is, I'm finishing very, very quickly. So because we have already overstepped the time for the talk, so we need to discuss.
Sorry, can I please add something?
Sure. Go with the question.
Yeah. So I have used neural net works in the iris data, and when use the neural network in the iris data, there is always some pixels where there is like a cosmic ray hitting, and they have an usually large value.
Mm-hmm.
But if you use neural network and try to recreate those images, then you will see that neural network will not show those cosmic data. Cosmic ray hits. And then I tried with something different. So I have given the network a completely garbage input. So some input that is only noise. It doesn't have any correlation between with anything. And then the neural network gave me just an average value, just a mean. Nothing else.
Okay, that is also something that I would expect to happen. Like if I feed network with no profiles, with just randomly distributed intensities, I would expect not to get anything back. This is something that we maybe need to also look in together and to discuss further. Yeah. Okay, so I just want to show you what happens then when I use this trained data to predict the whole field of view. So this is basically the fit. So I asked the network, okay, now interpret all the observations, interpret all the pixels. and then I get the models back, and then I feed these models back into inversion code just to calculate the spectra. And this is basically at the continuum. This is how you would see this piece in the continuum, and in the course of 3 spectral lines. I used 5 in total, but I wanted a big picture, so I cut to only 3. This is intensity, this is circular polarization. So you see that things agree quite well. I mean, probably if you looked into detail, you could see some, you can find some artifacts, like for example, okay, people online, they cannot see this, but I'm pointing here at one of these blue features in the Stokes V, which in the original is completely full. In the neural network, it has a white space in the middle. And this is because neural network was not trained on the examples which had so much magnetic field. So it doesn't know what to do there. So basically the proper thing, and how I want to repeat this, is to make a representative set of the profiles, to do some clustering, extract 10% of the profiles or 20% of the profiles. And I mean, in the future, we will have so much data that we can use 1% of the profiles. But we need just to sample them well, invert that, train network on that, and then network tells you what's happening. So I hope that by the next meeting, I can give you some updates on this. And this actually agrees very well. The fit agreement, when you calculate chi-square, it is not as good as what inversion would obtain, but it's not way off. All right. And then what you can do, and the reason why we do these things on the synthetic observations from the MHD cubes is because we can test if our inference is good, if we are getting back what we expect to get. So here is here's the comparison between the simulated values and the inferred values at 3 different depths in the atmosphere. And we can see that for the temperature, it's deep, it's sort of okay, but as we go upper in the atmosphere, and the upper in the atmosphere is also upper in the slide, it's pretty, it's not nice. But we know already that these spectral lines that I used here are not perfect for the temperature diagnostics. But if you, for example, look at the velocity field diagnostics, the maps look much, much, much nicer. So there is no fundamental difference between, so on the left is MHD, on the right is neural network. And when you compare these results on the right, again, with the inversions, so with inversions with the full field of view, there is no fundamental difference there. The relative difference is between what neural network gives you and MHD cube, and what inversion gives you and original MHD cube. They are of the same order. So basically, we are fundamentally getting back the same thing in this particular example. So it doesn't have to work. Of course, if you train the network on the quiet sun and you try to interpret the sunspot, you're going to get some ridiculous results. And the similar thing is for the magnetic field. So you can see that the structure of the magnetic field is more or less well recovered. We can see the same features. And of course, probably if we had some really complicated structures which were not appearing in the training data, your network couldn't be able to capture that, but it does relatively good job here for these things. Okay. So of course, the future steps, as I said, is to simply pick a better training set. But actually what I want to do now is I want to train the network on all this field, and then to take a local dynamo simulation, so different MHD cube, and to see how well the network is going to behave there. Okay, so this is the end. And I just want to repeat what we want to do today. So I showed you what science I'm doing and will be doing in the upcoming months. I showed you some things, how simple you can start. Of course, I don't understand almost anything of the intrinsic things of intricacies that are happening with these neural networks. So that's why we are starting these meetings. And but you can all start more or less now. And also in the email, I will share some GitHub pages of some people who are doing neural networks. And we had a longer talk than 20 minutes, and we have some science discussion. So now let's have more questions regarding the talk, and also questions regarding these online seminar series in general. So we have a question here.
Did you do your calculations on your own laptop or use some like custom machines, because I think it's very computationally expensive?
So the question is whether I did this on my laptop or on the cluster machines.
Yeah.
For this, this is a relatively small training set. So this, with like 10,000 examples, you can train on your PC in less than an hour. Okay. This specific model. if you have a bigger training set and you have more complicated network, you can use GPUs, and in GPUs it goes ridiculously much faster.
Okay, one thing that you use some data for training purpose, and again you use the same data for testing.
Yes. So the question is whether we use the same data for training and testing.
But if you use the different data, like you train the neural network with coefficient data and test again the network with coefficient data, but different from the training data.
Can you repeat?
Suppose you train your neural network with some coefficient data.
Okay.
And again test the network after training with different coefficient data.
Yeah, well, so the question was what would happen if we train the network on quiescent data and then we try with a different quiescent data? Yeah, so Mark is asking the next question. So I just finished answering here. No, that's basically this next step, except I will do it with the synthetic data. So I will train on this quiescent simulation and try to use it on another quiescent simulation to see what happens.
Now, because you use the same data for testing purpose, then what will happen? The computer will remember the minute details of your training data. And again, if you test your network with the same data, you will remember previous information and he will give you some results.
Okay.
This is not reality actually.
Yes.
It will be some artifact.
Yeah, yeah. So the remark is that if we test on the same data, yeah, I agree, of course, that if we test on the same data as we trained on, it's not the reality. But I was just intrigued by appearance of these here, of these smooth maps here, that it's sort of, because the only reason why I did this was to basically check how well the network was trained, not to really, I didn't expect this to tell me how good the network is on its own. I just wanted to check how well it is trained, and then I plotted these things, and then I saw something that sort of surprised me.
Another thing I think, because of the results are smooth, I think this is because of back propagation algorithm.
Okay.
Because neural network functions, if you give the input, it will give you some output, where if the activation function is sigmoid in the output layer. And in the hidden layer, we use the yellow activation function. This is yellow activation function birthday ignores the negative elements in your image. It will only welcome the positive elements.
Okay.
And later it will be the sigmoid. And then when the output will appear, it will again calculate the error and it will backpropagate the error in the previous input. And that's why the neural network strains. I think because of that, you got the smooth. I am not sure.
Okay.
But I think this error propagation algorithm works in that way that it removes the noise. Basically, I think sigmoid activation function, this is in the output layer. It actually helps to remove the noise.
Okay. So I will just I will just condense if the people online didn't hear. The remark was that the smoothness in these maps is the consequence of the backpropagation algorithm and the type of activations, right? Yes. So one way to test this would be to change the other types of activation and to redo everything.
Yes.
Okay. Okay.
But at least in output layer you have to use sigmoid.
Okay, so in the output layer we have to use the sigmoid.
But in hidden layer you can change.
Okay, so in the hidden layers we can change this.
Yellow or sigmoid, or there is some side variable function that also can.
Okay. Okay. So we have Mark now asking a question.
So as we've talked before, I'm concerned that we're not optimizing these inversions for structure in the vertical. So I was wondering, my understanding is that you trained on the smooth inverted atmosphere. Is that correct?
No, not really. Because, for example, as you see, this is not a smooth inverted atmosphere.
No, I mean vertically. You trained on the nodal solution to the vertical atmosphere.
Yes.
So can't we take a simulation and train on the actual structured vertical atmosphere?
Yes, we can, but I don't know what is the optimum thing to do there. So one thing, and I think Andres is maybe trying that, is to somehow map basically the images at different wavelengths with basically images at different depths to really relate wavelengths and depth somehow.
So what if we just take one snapshot from Urim, train on every column, synthesize a spectrum for every column in that snapshot, and then invert the spectrum from a snapshot, sometime later when the atmosphere is fully evolved, and see how well we can recover the second atmosphere from the training set from the first atmosphere.
Basically, you're proposing not to use smoothed atmospheres at all, to try to
train on every column out of a Urim atmosphere and ask, can we recover a second Urim atmosphere from the trained neural network from the first atmosphere? You
can try that, and it is a relatively easy thing to try, but the thing is that I was initially afraid to do that because as always, the biggest problem in inversions and the reasons why we use all this depth irregularization was that the radiative transfer problem is such that two neighboring points usually have a very similar way of influencing your now I'm talking points in depth. So these are fine samplings, and then two neighboring points influence the emergent spectrum in the same way, and then I cannot constrain them well enough.
Right.
But again, maybe we can somehow.
So what I suspect is what will happen is that at the inversion, the neural network inversion of the second atmosphere will be a vertically smooth version because there's only so much information in the spectrum, right? So you'll end up with an optimally vertically smooth atmosphere because the neural network only sees as much information as there is in the spectrum.
Well, it is easy to try. I can try that in the following weeks. And basically, the only thing that you need to try for that is to have a cube and the synthesis from the cube. And then you maybe split this cube in two parts, one for training, one for checking what's happening, or two cubes or something like that.
Yeah, that'd be great.
Okay.
If you would use the output of the neural network as an initial condition for the inversion, would it speed up the process considerably?
Yeah, so Hape is asking what would happen if we use the results of neural network inversion to initiate the inversion. Yes, actually that was my original idea, but then in the end I saw that results are already very good. But yeah, what I basically do now is I feed these things back. And now what I want to study is whether this spatial smoothness will be conserved, whether inversions will find that the minimum is actually in this, and if the minimum is actually in this grainy solution here. More questions, more comments? People from online?
I
please.
wanted to add on the importance of this validation set, but maybe we can discuss it later also. But basically, without validation set, you cannot be sure whether your network is under or overfitting. And you want to achieve this optimum, and that's why it's needed.
Yeah, the remark is that we need to use validation, and here I use validation, but I use like 20% of the data for validation.
Then it's correct, but it needs to be separate data set. But I guess Keras has a built-in mechanism of separating.
Yes. Keras has a built-in
validation. Yeah, then you did it correctly, but I saw you had this number of epochs, 100. I'm not very familiar with this Keras, so does it really? This number indicated to me that it just ran it 100 epochs, but it should stop actually at the point where the validation error starts to increase, but the training error still, of course, infinitely always decreases.
Yeah, so once again, for people online, the remark is how to stop the training procedure, and in principle, what we should do is follow the validation error and stop at the moment when it starts increasing. I don't
find the minimum of this, but maybe it's built in to this Keras library.
No, Keras is not stopping there. Keras does the number of epochs you give it.
Yes, so I think you should build some for loop around it and check this validation error constantly, and then stop when you.
Okay. That's a very practical and remark. More questions from the room?
Ivan.
Yes.
I had a question. I didn't get one part, maybe I missed it, but how exactly are you providing the input to the neural network? Are you giving one full cube or subset of your complete inverted cube, right?
For the training, I give a subset of the inverted cube.
But it's a cube that includes spatial and spectral dimension.
Yes.
Maybe you want to try giving it just spectra from one pixel and ask it to reproduce just the atmospheric parameters for that pixel. And then you do this independently for all spatial pixels.
No, but it is done that way. Yeah. It's not learning cube pieces separately. It's learning it's learning spectra by spectra, and it's interpreting spectra by spectra.
Okay, right. Thanks.
Do we hear more questions online?
I have a question. I just connected. When did you start? I thought you were supposed to start now. Did I miss something?
You missed everything. You are in the 1 hour later time zone. No, but we recorded it. No, I didn't figure out that you are not here. I'm so sorry.
No, it's my fault. Okay. Sorry about that.
Sorry, Hector. Sorry, and it is your stream, and then you were not there. Oh,
this is embarrassing.
No. Okay, more questions online? Would anybody like to comment on the future meetings and what you would like to hear and what we could do differently, except having a working mic so that people from the room can ask questions which everybody can hear? Anybody from the room wants to add something?
Technical details.
Technical details.
Yes.
More technical details.
Yes.
Okay. So we will keep this in mind. So I will pass that to Andres. Okay. Then there is another thing. We already spent like 1 hour. I hope you had a good time. So basically, I propose that we stop now because maybe pushing and informing discussion longer than 1 hour is not suitable for everybody. So I will now ask you to contact me somehow in the upcoming days, because I want to have a sort of mailing list or something. For example, for the moment, I have a very preliminary mailing list of some people who I met during Hinode and knew from Twitter, basically. So what I want to do is maybe we should have a mailing list where, like a proper mailing list, where we can share resources, and then whoever is bored with the mailing list, they can make a filter, and I think it is much better than simply having a list of people there. And it is also something where we can repost the questions and summaries of the talks, so that people who didn't attend and just want to skim through it, that they can see. Does that sound? I hope that sounds as a good initial move. Okay, so then I can, yeah. Okay, so in order not to hold your attention anymore, we continue the discussion online. This is going to happen again in 2 weeks. Andres is going to give a talk. I don't know exactly which day it's going to happen, but now I will have much more contacts, and we can pick. It will probably be some term like this, but I want to ask everybody online and also everybody here who is from Europe that it would be super nice if we could move this later, so that people from US and South America, because Francisco is also maybe somewhere out there, for those of you who know him, is much, much easier if we start at like at least 9 their time, because now it's in Boulder, it's 6 in the morning. And also in some months, I'm also going to be on that side, so yeah. Yeah, anyway, okay, let's not take your time anymore. We continue the discussion online. We can also get in the individual contact. I'm going to discuss here with our guests from Vector Magnetogram Workshop. Thank you all for listening, and see you again soon.
Thank you, bye-bye.
All right, thanks.
Hey, Ivan, before you go, are you still there?
Yeah.
Okay.
Do you think maybe Slack would be a nice alternative instead of emails?
I think so.
Because it would be much more organized and much more readable than emails.
Yeah.
So